All right, we'll get started. People will jump in. So, welcome to Drake's Lounge, Australia, and some new information is we are still planning on going to Owens Valley for the Western Conference in March. If you guys get up to that, or at least we'll have the links in the Sarah's store to be online for that. Nice thing about Owens Valley is you can walk right up to the antennas, and we're actually having the meeting, feet away from the operations center equipment. So we can all look at that. And with that, Steve, you have some kind of live demonstration.
Well, it's been long in coming. There wasn't too many people turned up at the last SARA meeting. Apologies for that. I wasn't there either. But one of our colleagues, Joe McGee, he presented a little video that I prepared. But I think it's better if we try to demonstrate our operating radio telescope live on the Zoom session. So if I can share the screen, I just got to make sure my desktop grabs the right thing. So I've grabbed this. So what are you seeing on the screen? A set of charts? On the left-hand side, are you seeing charts?
I see blue and red on the left. Yep.
Those charts? Okay. All right. So that's a live link, internet link from my home here in the eastern suburb of Melbourne, up to 100 odd kilometres away to our country property at Heathcote, central Victoria, using the internet and the satellite link down to the property at Heathcote is from Elon Musk's Starlink system. So that's how we're linking into the system up at Heathcote. And we're going into the laboratory, our radio laboratory, near our big 8.5 metre dish. And there's a series of desktop computers. And I'm logging in to a desktop computer. So what this is showing on this particular computer is the status monitor of the receiver up on the tower, on the dish. I went to a lot of trouble, you might recall, stabilizing the temperature of the low noise amplifier and the front end box. The low noise amplifier is quite a small metal box, which is a lot easier to chill. So I chill that down to 5 degrees, but the front end is a much bigger die cast box, 6 inches or so. And I only chill that to 15. So it's a bit hard to see the detail in this graph from the live measurements. So what I'll do is go to a different screen capture where I've been capturing those daily results of the status monitor. And I've then been keeping an eye on it on a regular basis. This is the one, yes. Okay, so I can zoom in on that, show you what these graphs are showing. So the top graph is looking at the power supply voltage and current. So there's a current sense, 0.001 resistor in the system up there, and that's feeding the results into an Arduino Nano, well shielded, thank goodness. So you can see the blue line is the supply voltage. That's flickering up and down occasionally because you got a voltage drop across 50 meters of DC cable. And you can see the current flicking up and down at the moment. On that particular reading, it was the last point of the day, which is 0.6 amps. And that's with no Peltier cell running. But when you see one of the Peltier cells comes on, it's typically 4 amps. But when both of them running for the LNA and the front end, it pushes up to about 6.5 amps. So with the higher current consumption, the supply voltage drops a bit, but it's always above 12 volts. And there's internal boost regulators operating the receiver. So it doesn't really matter too much if it drops but even below 12 volts. So I'm quite pleased with how that's operating. But you can see the Peltier cells turn on and off quite a lot through a 24-hour period. So this is 0 hours back to 0 hours, 24-hour period. So the next graph down below that is the air temperature inside the receiver cabinet. So it's a big box up at the feed point. And we draw air from the outside through that cabinet, and we push it through the fans that are cooling the heat sinks on the Peltier cells. And the outside of those fans goes through a set of ducts that blows it out a separate part of the box. So we're monitoring the airflow through the cabinet And that gives us a reading of the temperature inside the cabinet. That may not be the ambient temperature, might be slightly warmer, usually is, and also gives us a reading of the humidity. And this particular set of results is captured there on the 1st of September. And that's still our late winter, and we're still having a long, cold winter in Australia, in the eastern states, that's for sure. So the humidity, which is that purple line, you can see it is reaching 100% for a fair bit of the day. So it's very moist inside that box. So the next chart down is the low noise amplifier. Now we've got two graphs shown there related to the LNA. One of this is the fan that's cooling the Peltier cell. So we're keeping an eye on the fan speed at all times. If that fan ever fails, you can have a thermal runaway on the Peltier cell. It just keeps getting hotter and hotter. So there is a cutout circuit if that was to ever happen. So we monitor that speed. If the speed stops, the Peltier cells, both of them will turn off straight away. But the more important thing is the temperature. So that little low noise amplifier, critical component in the receiver, sitting around 5 degrees. And I hope you can realize that's very much flatlining through the entire 24-hour period, which is brilliant. Really pleased with that. So the next graph down is the temperature and fan of the front end enclosure. So that's a much larger box. We only try to cool that to 15 degrees. And when it goes below 15 in the ambient, then it'll just track the ambient. The Peltier cell will turn off. So you can see there's a lot more temperature variation of that front end enclosure. But still, it's only about a 5-degree change. And I've got relevant curves that show the variation of the receiver gain based on these temperature changes, because I did calibrate that some time ago. So the other thing I'll just quickly flick through, this is sort of like day by day. There's the 3rd of September, the 4th, the 5th. So I've been capturing daily snapshots of the performance. Now there's a particular interesting day on the 7th of September. Both the LNA and the front end were just basically flatlining within a degree of the temperature. So I'm very pleased with how that system is working. So if I go back to the radio telescope live again and switch to another thing I want to show. So, right, so that's back live again, looking at that status monitor. And down the bottom left, I can select the calendar date and load that file. So we haven't lost the history of all those previous days, even though I've been doing screen captures for my own record. That's just for safety, really. So the system up there is storing each day as a separate file. And the most current one down here is the 27th. I can load that. Sometimes when I log into the system, there's nothing on the screen. That's just a case of refreshing the browser. It's a browser on the desktop. So that computer is dedicated just to looking at that status monitor. And I do that on a regular basis. I can even access that system from my mobile phone. Just click a couple of links, put in a password, and I've dialed into those computers up at Heathcote. Now, down on the bottom left of that screen, do you see that little window I'm about to open? Someone give me an answer there, just to make sure I've got it all sharing the screen.
Go ahead.
You can see that I'm about to click on that one on the bottom. Okay, so when that
Yep.
comes up, now, okay, good. So now we're accessing the 2 control packages of software that Dr. Tim Davis, a great member of our team, has prepared for us. We wouldn't be anywhere without Tim, who's written this software. So this is the control and receiver data collection part of the radio telescope. So in that view you're seeing there on the left-hand side is a planetarium type software package. Tim wrote that package himself. It's got some limitations, but we're working around them at the moment, and he can see ways of making improvements, and I've provided some feedback as well. On the right-hand side, we've got a spectrum chart, amplitude in the vertical scale, frequency on the horizontal. It's calibrated in megahertz at the moment, frequency. So there's the center frequency is 70 megahertz, and that's the super heterodyne downloaded frequency conversion of that front end receiver from 1.4 gigahertz. It's the RAS, Radio Astronomy Supplies SpectraCyber receiver, basically, if you may recall that. So 70 megahertz output. But Tim has put in a calibration there. We can switch that mode to Doppler shift. So we can read directly off the screen, hundreds of kilometers per second of Doppler shift. Now, the signal at the moment, it's just a live signal. It's jiggling around because it's the noise background of the receiver. There's a bit of a bump at the neutral hydrogen frequency, slightly negative Doppler shifted. There's a spurious response there. This particular receiver is the RSPDX, quite a good software-defined radio, 14-bit resolution. But I am aware now, I did some more detailed assessment of that particular receiver just during the week using a signal generator and home setup. And I've discovered that there's a number of spurious conditions that can appear in the result. And it can also be the way the software is applying its features to that. So we have to be aware of some of these little spurious problems. This is quite a wide span. If I go to this other tab on the system there, radio, so that bandwidth has been set to 5 megahertz. If I was to flick that to 1.5 megahertz, redisplay the signal, you can see that it's been narrowed up to a much narrower bandwidth for the receiver, and that spurious is gone. So there's another way to deal with the spurious, just change the receiver bandwidth. The other thing that's happening on that screen is the pattern down below. I'll go back to 5 megahertz, the pattern down below the spectrum display, and that's the waterfall display. So Tim has created a conventional waterfall display. That's a little bit clunky as well, but we can see ways to improve that. Now, as you can see, this display has got a button there called gain correction. If I was to take that off, the display goes into a distorted mode, slopes on it, other extra little bumps and so forth. That's because we haven't corrected the shape of the output based on a noise reference. Now, I'll put that back on again. So a previous result captured the data of the noise generator and then use that to subtract from the receiver output. And that creates a leveled, corrected response. The other thing we can do is to switch on an integrated measurement where we average that waveform over 15 seconds, and that cleans up all the noise. And that's a much nicer pattern to look at. Every so often, every 15 seconds, you'll see it's just done another average then. So you have a little burst of noise and it'll settle down again. So the noise source is the SpectraCyber broadband reverse bias diode noise source. We can switch that on and off. I won't do it in the live demonstration. There can be a few hiccups with this if it doesn't happen properly. And because I'm got multiple links running here on my home internet, I might muck this up. But suffice to say, that's the way we switch the remote noise source on. When we do that, it disconnects the antenna, the receiver low noise amplifier from the antenna and goes to this noise source. The reference level here in the spectrum display will go up to a much higher level. It's about 4 dB above the noise floor. You then get a snapshot of that noise source, and that's what you use to correlate and subtract from the background, and it irons out all the ripples and bandpass characteristics of the receiver. Great feature. I'm not sure what else I can show. I can show the dish. If I go to the dish control tab, this is looking at all the mechanical and electrical features of the control system of the telescope. It also has a summary there of those status monitor. Again, the front end temperature, low noise temperature, low noise amplifier temperature, the fans. So it's like a snapshot rather than the graph of the status monitor. And there are other things on our telescope that we've got to manage. There's a lot of limit switches, safety switches on the gates and the that sort of thing. So we're looking at all of those. And this is how Tim has set up his file management system too. So we capture a result, we set up folders, we save the file measurements to a folder with a file name. That's all done here as well. I can control the dish from here. At the moment, the dish is that little red dot over there. I hope you can see where the cursor's pointing. And let's try something. The way the program works is you put the object which you want to go to into the center of the screen, and you use like a grid pattern here. You can set up the size of the grid, and the center cross section of that grid will be where you're sending the telescope. So given the scale of this screen at the moment, I'll just use that point there, but I was going to head towards the Small Magellanic Cloud. That's that pattern there. So if I switch, what we do is to get that location, we just go read from chart. So it's found that location in the center of the screen from the chart, and move Alt as. So if we push the move Alt as, the telescope will move to that central location and start tracking. If we push if we push it to Alt as, it'll move to that location and stop, just stop physically at that altitude and azimuth. But if we chose RA Dec, it will move to that location and then track it. So I'll push RA and Dec. And did it work? Yes, you can just see the telescope, the red dot starting to move across the Milky Way and heading towards the south. And it'll eventually end up there. That might take a minute or two. What I was hoping that we could also show is a camera. We have cameras pointing at the dish, so anyone who operates it remotely will be very much an advantageous thing to have, where you could look at the dish moving and there was no obstructions in the way or children hanging off it or something. I'll just stop that screen share while it's moving, and I'll show you a couple of other photographs that are relevant. So if we did have that camera set up, it would look something like that. So that's our dish as it stands today. We had a star party up at the property last weekend. Very nice turnout, lots of people interested in radio astronomy. So we took them through the laboratory and explained a lot of things to them. As we might get some new members that way. So this is the jack screw that lifts the telescope up and down in altitude. Remember, we had a lot of trouble with that over the last few years with the worn out drive gear. Well, that's all good and solid now, and these concertinas that collapse and stretch are protecting the steel jack screw, and it's well and truly greased up, so we don't appear to be having any environmental problems now degrading that system. So we hope to get several years out of that, and maybe decades before it needs any major servicing. The other thing I was going to show is that we've added some more features up at our property at Heathcote. And this is the clubhouse. On the side of the clubhouse is our main two-phase power that comes into the property. But this is new. This was installed only about a week ago. And what we're looking at there is a battery backup system, a huge battery backup system, which is fed from a solar panel system on another building on the property, which is the accommodation and amenities for the visitors. And on that panel there, you can see a display. I'll zoom into that. So that's a touchscreen display. You walk up, touch it, and this lights up, and you can see these are animated graphics of what's going on. On the right-hand side, you can see the indication that, you know, it's a photovoltaic battery 5 kilowatt charging system. Charging up a battery at that stage, it hadn't even reached its full charge, 21%. Charge can come off the main grid, but it's mainly going to be coming off the solar panels. And the load that we were running that particular day on the property was quite light. So here is a paradigm shift for our property at Heathcote. It's always been plagued a little bit by power failures that cause everything to fail. And we've often got to try and get the system back up again, maybe even a 3.5 hour drive to go back up to the property to turn things on and off and get it working again. generally speaking, most of the electronics in our laboratory up there have successfully come back on when the power has recovered, but not always. So it's a new era for us now to have battery backup. And that property, that part of Victoria is often referred to as Lightning Alley. We do get thunderstorms that come through and they can just pull out the grid for a couple of hours. So hopefully we don't have that problem any further. Now, I've just got to get back to the telescope again, that one there, I hope. Okay, so that the telescope's still moving along. You can still see that happening there. If I go back to the signal, just go back to live signal rather than averaging. So you can see that spurious is gone. That spurious may be related to something in our laboratory. We've got a lot of equipment on the radio lab, a lot of environmental sensors, other citizen science things that we were contributing to. And we found some of them generate locally around the laboratory. They generate radio interference. So there is a move again in the next 6 months or so to shift a lot of that stuff away from radio astronomy. It's earth sciences, and if it's causing interference to our big dish, we don't want it. So that's going to end up somewhere else on the property, and hopefully some of those spurious signals that you saw won't be there. So yes, it is taking its time to get down to that spot. Perhaps we won't dwell on it much longer, but there you are. Isn't that an incredible piece of demonstration of technology at our fingertips? Zoom session internationally, me using the same laptop to locally control a radio telescope dish managed by a bunch of amateurs, and the telescope's over 100 kilometers away from where I live. I hope you appreciate it blows your mind, all this technology sometimes. There is another step that I would like to demonstrate, but it'll have to wait. And that's the actual collection of data and the post-processing of the data. The way Tim has set up his program, it's not to say do a drift scan, although we can do that. It's not to say scan the whole sky and produce a massive amount of data and dump it out and process it. Tim's methodology is to create a grid, and I can turn that grid off, turn it back on again. So, and if we were to then start collecting data, it would start on moving to the points, the intersections of these points on the grid. And you typically would decide to set up that grid based on the aperture or the beam width, or half the beam width of the dish. The dish has got a 3 dB beam width of 1.4 degrees. So you might set up your grid for 0.75, for instance. That's all adjustable with these panels up the top here. So it will take a measurement, 15 seconds, move to the next one. 15 seconds, move to the next one. And so it might take several seconds to move between one spot and the other as well. So they might take a while to build up that measurement. And there's a button there called path. So you can see the path that it's taken. And Tim has optimized the program there to minimize use of the jack screw. That's the mechanical lifting. That we would rather do that in one step at a time for a number of measurements rather than going up and down, because we do know mechanically that's a slower process, and it's also one that wears out the mechanism more. It's much easier to rotate the telescope in azimuth, and we do that as a preference in the algorithms to take the measurement. So there we go. We could have a chat about other things and come back to me. I would like to show what it looks like to bring the Small Magellanic Cloud up on the screen, and what will appear in the spectrum display is a Doppler shifted image. So at the moment, we're just seeing residual background levels from neutral hydrogen from the Milky Way. The intensity's dropped a bit because we've gone off the bulk part of the Milky Way. We're into the getting off axis now, so the levels are much lower. But yeah, there is another aspect of the program, and I won't be able to demonstrate it this morning. And that's once you've collected data from this grid, then you may want to plot it out and analyze it. and Tim has written a program to do that. So I hope you can be patient, and once we've done some studies ourselves, we'll be able to present that to you, because there's a number of features in his plotting program that are interesting as well. All right, so I'll stop there. And in the meantime, while we're chatting about other things, I'll get this queued up on the Small Magellanic Cloud and we'll have a look at that. Thank you.
Great work. Any questions for Steve? So, Steve, we had a Spectre Cyber here at DSCS in Colorado, and Ted Klein actually used some of that data, the format of a standard Spectre Cyber for the EZRA input. Is that stuff that you could share when you start doing these analysis, or you start collecting the Spectre Cyber data? Just send those text files to us, and we can process them with our system.
I'm not entirely sure it's compatible. What we're doing is taking the receiver output, which is just a signal, and we're post-processing that completely independently in a different program. We're not using Spectre Cyber back-end software.
Oh, okay. All right.
Yes,
Then it's probably not the same then, yeah.
Custom software by Tim Davis, Dr. Tim Davis, who currently is in Stuttgart, Germany, doing paid research. He's retired, but the German government are happy to have him do research for the university. What a nice job. He'll be back in October, and he's keen to come back and kickstart the rest of the work we got to do. But we'll happy share whatever we get, and certainly there are like, you can't see the Small Magellanic Cloud from where you are, can you?
No, we can't. I heard about it in astronomy class, so that's about as far as I go.
So the process has begun, gentlemen. We don't have a reason electromechanically anymore on the dish. That's finished. So now it's fine-tuning some software packages, but in principle, the data can be collected. We can put some faith in the data because of that temperature stability. And very happy we're at this point now. It's taken a number of years, but we're there.
Oh, yeah. Yeah.
Steve, I'm excited. That's just exciting. You got all this stuff going. Congratulations.
It's been a lot of work, Ted.
One question is fan speed. How do you get the fan speed number?
Oh, well, it's a very good quality fan, and it has a tachometer output.
Wow, on the fan.
Yeah.
So it's just not current or something.
There are many different types of fan, Ted. There's two-wire fan, which is just put power on it and it spins. There's a three-wire fan, and the third wire is the tachometer, so it measures the fan speed. And then there's a four-wire fan, where you can control the fan with pulse width modulation. And I've done electronics for other projects where I've used any one of those types. So the three-wire fan's very common. And the one I chose has got, I think it's a magnetic bearing. And there's due to last 15 years at 40 degrees centigrade. So it's a long life fan. And under the conditions we're operating it at, it'll probably last much longer than that. So continuous operation, I don't expect the fans to fail, but we are monitoring them because they're critical. If the fan stops spinning, then the Peltier cell has to shut down.
Very neat. Okay, I got to start shopping in better shops. Very good.
I know. Yeah, I've only seen a two-wire fan, so yeah. Okay, Paul just came back on. Paul, we only got to Steve. You have a great my presentation, so I'll give it back to you.
Hi, everyone. Sorry I'm late. I'm not sure what I've missed. I'm sure Steve's given you plenty of information. As far as I'm concerned, from my point of view, I've just been chasing. Oh, well, first I should show you where I am, I think. Because how do I change my camera? I don't know how to change the camera in Zoom. Oh, there. There we are. That's my current location. See, with the boats going by just on time.
Looks pretty nice, Paul. Glad you're working so hard.
Oh, it's really hard work here. Yeah, this is oh no, that's not so good, that position. I think the lighting is all wrong. This is up in the Hawkesbury. That's the Hawkesbury River, which is just northwest of Sydney. So from Melbourne, it was about a 10-hour drive, and it'll be a 10-hour drive home on Monday. We'll do it all in one go. Quite a long way, but we just take it steady and we eventually get home. This is the third time we've been up here, and to this same place, in fact. It's a great location. It's away from the world, and I could highly recommend it if any of the, well, certainly to any of the Australians, but if any of the US people end up in Australia, I could recommend coming up to this location. Just only an hour out of Sydney. Great spot. So the main thing that I can report on is the Muon Detector project, EduMod and MDetect. MDetect is the company that's making these muon detectors on a commercial basis, so they're used for industrial purposes. They're associated with Swinburne University in Melbourne. And EduMod is the educational arm of the Muon Detector project. So the concept is that these units are lent to schools or bought by schools, and they then run a project. It'll run for 5 days. So everyone turns their detector on and collects data over the same 5 days. And then you do that goes into an Excel spreadsheet. You then average over the 5 days to get a 24-hour plot. And then that all goes into a database, and schools can then compare their data with one another. And the idea is to get a wider range of locations as possible, certainly in the first instance across Australia, and then in the longer term to set up and collect data from around the world, different locations around the world, to get some comparison about muon flux. My graph so far has shown certainly a peak around midday, which suggests that the sun is involved with generating muons. So the muon flux rises as the sun is higher in the sky. The muons are generated in the upper layers of the atmosphere, right at the as soon as the cosmic rays hit the atmosphere. And they're very short-lived particles. They should never get to the surface, according to Newtonian physics. Distance equals speed times time. They should decay before they get down to the Earth's surface, but they don't. We do detect them. So this is one of the elements of proof of Einstein's theory of relativity, because they're traveling at 0.99 something the speed of light. Their time dilation comes in. So as far as we're concerned, their clock goes more slowly. They last for longer than their 3 microseconds or 4 microseconds or whatever. And that gives them time to get down to the Earth's surface. From the muon's perspective, the length contraction occurs. So they are stationary, the muon is stationary in its own frame of reference, but it sees the Earth coming towards it at high speed, 0.99 the speed of light. And so the distance between the muon and the Earth is shortened, relativistic length contraction. So either way, from whichever perspective, the muons get to us, and we get them. We can count them. So the Astronomical Society of Victoria had a couple of committee meetings I've attended 2 meetings so far. We got very close to them agreeing that they would fund the purchase of one of these units so that the ASV could install one out at our radio astronomy location at Heathcote, north of Melbourne. Steve's probably been talking about that now. That's where our big dish is. The idea would be to install it there and stream the counts over the internet so that basically members of the public could use this data. And so then we got very close to agreement within the ASV committee. Then they deferred it because not everyone was there. And then so we had a second meeting, and we got very close to getting agreement. And once again, it was shelved. And now ASV, the Astronomical Society, is talking directly with MDetect, and we'll see what comes out next. So next meeting, I may have a further update on what is happening in that situation. It's a great addition to the detectors of various sorts that we've got at Heathcote in our radio astronomy observatory. But we're just battling with the money at the moment. I'm not quite sure where all that's going to head off. Steve, did you have something to add to that?
Well, they're not all that cheap, as far as I know, too.
Cheap, no.
And I think there's a bit of a political issue with the ASV. They would like to see the radio astronomy section deliver something before they give us more money. So we have delivered. We've now got a working telescope, and I did put in 30 minutes or so, Paul. I gave a live demonstration of the telescope working with remote access.
Okay, I shall watch on the video.
Yeah. So if we get this detector, a muon detector, it may not end up bolted onto the radio astronomy area, because we have found some of these citizen science projects can generate radio interference, believe it or not. And I've even seen harmonics right up at 1.4 gigahertz. So it may end up on another part of the Heathcote property. And we're looking at one of the optical telescope sheds that's got power in it and an internet connection. And that's 100 meters away. And it might be more advantageous if we install all of that citizen science stuff over there and we dedicate the radio lab to be a quiet area for the dish and the other. So it'll still end up getting installed, I'm pretty sure. Just pops right at the lab. But I guess our team will be the ones that manage it as well.
Yes, yeah. And also, I think, it's a portable unit. So when we do regional outreach, when we go to other locations, or there's something on at the Caulfield Racecourse, that those events, those public events or club events, the unit can go and be demonstrated. It's a very easily portable. It's laptop driven, USB powered. So you just plug it in the USB port. So it's very portable, and I see it as an educational outreach as well, that schools could make use of the unit and collect data on an individual an individual school basis. So the portability is a big plus. Yes, it is an expensive unit, and I think that's part of the negotiation that's going on at the moment to see whether something will, we can do something on the money side. So I don't know. It's a work in progress still, and there are other kits around. There are some kits. There's one put out by the UK amateur radio astronomy group, but it's a build it yourself, and the question would be sourcing the parts, all those sorts of things. I think we've got enough skills within us to build it, but it will be getting hold of all the parts. So that's something to explore as well.
So these muon detections are different to radiation, because we have a radiation detector up at Heathcote that's been running for a couple of years now.
Yep.
So that detects gamma rays and
that's right.
Beta particles.
this is two parallel detectors. So the theory is that the first one detects everything like the gamma rays and so on, as you're saying, but they then don't get through to the second detector. So the algorithm is that if the second detector detects something simultaneously with the first detector, then that's a muon, that everything else has been absorbed, alpha and beta and gamma, or whatever that would be around it, has been absorbed.
A lot of unwary are also shocked to realize this stuff is passing through our bodies at all the time.
Absolutely, yes. But that's part of the issue is that the interaction with matter is so small. Chris, I think, was saying in the meeting the original detection was via a cloud chamber, and because they are charged, they're just basically heavy electrons. So they do leave a track in the cloud chamber. I found a picture of Anderson's cloud chamber that was used to detect it in the first instance, and it was going to be a bit more expensive than the Muon detector from MDetect. So I think on that scale, it's a very robust system. It's very reliable, and it is a commercial standard system. I've suggested that they might build some smaller ones, because once they've got the electronics worked out, then just build it with a smaller area detector. But we haven't got that over the line yet. So
hey, Rich, go on, Paul.
Yeah, carry on. No, I was going to hand over.
I was just going to say I've got the telescope on the Small Magellanic Cloud now, Rich. If you want me to share the screen of that observation.
Go ahead. Yeah, Paul's in charge now, but go ahead.
Yeah, go ahead, Steve. I'm just observing at this stage.
Well, Paul, this is a live screen capture of the dish up at Heathcote, and I'm manipulating it and controlling it with my cursor from the same laptop that I'm using for the Zoom session. I just clicked it over to Alt Azimuth because all right, now I go to there, move to RA deck. So now it's tracking. So what's on the screen, the red dot, is in the middle of the Small Magellanic Cloud. The telescope's tracking that.
Yep.
And there's on the top is the spectrum display. So 0 kilometers a second is the Milky Way Doppler shift. The intensity of that trace is now diminished because we're off axis from the Milky Way. But have a look at what we've got here. This signature is the Small Magellanic Cloud. And it's also interesting to see that there's a double bump.
Yep.
So, and that's at about there's 100 there, 200. It's about 180 kilometers per second negative. So it's going away from us relatively. And it's also apparently rotating. Marvelous. I think some of these observations that we've been making, Paul, are the first.
Yes.
We've fine-tuned the receiver to the point where we can see these details now. So there's a lot more we can do. There's little galaxies that we could look at. We'll even try the Andromeda when that starts to get a bit higher up in the summer at our time of year. So there we go. It's working, and the waterfall display is showing those higher traces above the background as well. Well, that was it for me. I was hoping to show you that very excitedly, and that's it. There we go.
Yeah, well, we finally got there. It's been a long journey. So that well, at least we'll be able to show the committee now that you do have something to show them and something to show the public when they do turn up for public days.
So Steve, get your PhD to use those results. Oh, seriously, to use those results to figure out, based on the angle of the Magellanic Cloud what the rotation rate is, compare it with the textbooks, and tell them, oh, we can do this. We can start doing this for real.
Yep.
And that is cool. And I need a journal article for that stuff, by the way, if you're going to show that, so that you can actually detect the rotation rate.
Yep. We do have a tendency to write lots of reports. I've lost count how many reports I've written. So it'll get documented for sure. And we're still going through a bit of a calibration process, Rich. And I need to have Tim back in town to help us with that, because we want to put absolute quantities on these things too, like how many Anskys are we measuring, that kind of thing, and what's the noise temperature of the antenna. And we'd like to pin down a lot of those background numbers as part of our assessment.
Yeah, Steve, this is Dick. I was going to ask you if you had in fact measured the noise figure of the system and the G over T and some of those characterizations. But before you answer, I wanted to just say that was a great presentation and you guys are doing fantastic work.
Not bad for amateurs, is it, Richard?
You got that right.
But to answer your question, not yet. We're working in that direction. It's certainly something we have to be aware of and be able to put numbers to everything.
Looks great.
Yeah, real progress, Steve. That's great news, and I think Phil would be happy as well. Now, Rich, I don't know. Have we been around the Australian members yet?
No, we just had Steve and you.
All right, very good. So I can see Joe. Joe is the next one on my screen. Joe, have you got anything at your end to report?
No, nothing, unfortunately. I've been off busy doing all the stuff. I'm not even getting to as many meetings as I would like, the Zoom meetings. So nothing from this end, just a promise of things will be done at some stage.
Very good. All right, thanks, Joe. And the next one on my screen is Rob Lucas. Rob, are you in Australia?
Yes, can you hear me?
Yes, we certainly can.
Okay, well, for me, I'm overwhelmed, and I think your progress is, very impressive. And size does make a difference, doesn't it? Anyway, what I've been doing is, a couple of months ago, I, remounted Alex Pettick's, Yagi antenna so that I could, point it, adjust it much easier and more accurately. And what I've done is I've started at 35 degrees. And I've been going up every 3 or 4 days by 5 degrees. And I'm now up to 60 degrees. And I've collected a bunch of data, but I haven't really stopped long enough to do the analysis of it. The next thing is last Sunday, I jumped on an airplane and I flew to Christchurch in New Zealand. And my background, if you can see it, is the partial solar eclipse from, can you see it?
Yep.
Anyway, that's the partial solar eclipse at sunrise coming up through the trees, from Christchurch, and then after the eclipse on on Monday, on Tuesday, we got back on the plane and we flew back here, and I haven't analyzed or put anything together with the pictures from the partial solar eclipse. And this afternoon, we go off to Macquarie University here in Sydney and we set up telescopes, visual telescopes, and do the Macquarie University open house. Okay, so so that's basically no data to show except the picture in the background, and that's where we're at right now. Lots of things happening, make it, but you guys in Victoria, are really out doing a good job. Yeah. And Hawkesbury is a good place to go. And just and where we went to in Christchurch was a golf club resort, outside of the city. Yeah.
Yeah, great place. I was there earlier in the year, May, in Christchurch, and another recommendation for our American friends if you're doing some travelling. Certainly, the whole of New Zealand. We were in the South Island, Christchurch and other places. Highly recommended. Great place. Thanks, Rob. Perhaps we get an update in a month's time. I think Duncan has headed off. He had some work to do. But Roger, I can see there. Roger Heap, are you with us?
Yeah. Can you hear me?
Yep, certainly can. We can't see you.
Okay. I have my start video on. You know, what's happening there?
Camera with a line through at the moment.
Yeah. Okay. Well, I've hit the start video. So don't know what else to do. Little lights on my camera, so my computer's telling me that it's doing it. I'll just click it a couple more times. Light went off. Light back on again. Anyway, you can hear me. That's the main thing,
We
I
can hear
guess.
you, yep.
Yeah.
Audio.
Okay. So I really don't have. Yeah. I say I can't really. Recording. No idea what's going on. Anyway, I don't really have much to report. I'm still quite busy at the moment. I think last time I spoke to Rob, I was had bulldozers and graders working on my road. So that's finished now. So if you want to come for a visit, Rob, you can actually get into my property a bit better now. But at the moment, I'm building kitchens and renovating a house that burnt down. So I'm probably going to be pretty busy till around Christmas time, I'd say. Unfortunately, my radio astronomy has gone backwards on. I've got several other things that I get involved in. So even my Super SIDS and my Radio Jove are all packed up in boxes in my shed, waiting to come back out again. But certainly very impressed with Steve's effort down there. That's really, really good. And we hope to sort of get up to some same sort of level. But gee, we've got an awful lot of catching up to do. So yeah. But there goes my telephone. I will just quieten that.
Sounds like you've
hold
got
on for a
plenty
sec.
on.
Yeah, got technology going off all over the place.
Yeah.
So you're not far from us, Paul. Some of the water from not far from where I'm at the moment flows out through the Hawkesbury. So welcome to New South Wales.
Yes.
Really don't have much more to say. So yeah, back to you, Paul.
Okay. Yep. Thanks, Roger. Perhaps another update in a month's time. Let's see how we go. Just on the busyness, I am planning to put together an article on my experience with the Muon Detector and show the results. So, Rich, that will be coming your way. But as usual, work has got in the way. I had 3 weeks at one school, then I did 4 weeks full time, which was quite a challenge. I haven't worked full time for 16 years, and this is the 2-week school holiday. Then after that, I've got two more weeks at the other school, and then we'll see what happens after that. So it's on the cards. I will get some time to create an article on the Muon Detector, but it might be a while yet, Rich. So I think that's it. We've lost a couple of others who I saw at the beginning, but I think we've covered all the Australian end as far as I can tell. So, Rich, back to you.
Okay, Pablo.
Nothing to report.
Okay, and then Pablo has been working with the ChaTGPT for radio astronomy, actually just using radios, some of the data, having it analyze some of the data. So we got some promising stuff in there, but some of the answers are a little controversial, but hey, we're having fun.
Well, if you want me to talk about that, I'll talk a little bit about that. While you guys were talking, I'm installing a second 2-meter antenna, and I wanted to build a scalar feed horn, and so I asked it, based on what I have, to design one, and then to create a 3D printer STL file to build it, and it did it just now.
Can you go through a couple steps maybe on screen? I don't think these guys have been exposed to your how to actually get into it and then make it ask a question like that and get some results.
Okay.
Quick demonstration.
Yeah. Well, once again, I'm experimenting. I'm not asserting anything. I am doing an experiment. Whether it's valid or not, that's to be determined. But that's what we do here. We experiment. So,
Pablo, some articles I've read, technical articles from amateur circles and so forth, that have asked ChatGPT a question, and it's come back with an answer, and it seems legitimate, but there are errors in there and mistakes and omissions.
yeah, it's called hallucination. Sometimes it hallucinates, but it also, you can correct it, you can train it, and you can make it better. It's just no different than a computer system or a program. And in this case, they're not called programs, they're called prompts. Of course, it will make mistakes until you train it properly, and then it won't make mistakes anymore. And it's able to, can you see this here?
Yep.
Yeah.
Equation. Yep.
So I just, my dish, I said, okay, my dish measurements are 83 inches in diameter, 13.5 inches deep. What's the focal length for the hydrogen line LNA? So it went on to explain everything, focal length, diameter, simple stuff. And it came up with an answer of 31.9 inches. Your focal length is 31.9 inches. That's very simple. Anybody can do that. And then the LNA placement tip for the 420 megahertz hydrogen line, and it came back to optimally receive the 21 centimeter line. The LNA feed horn or dipole should be centered at 31.9 inches, which makes sense. It's nothing out of this world. The tripod mount. So I said, okay, I didn't know what a scalar feed horn was. So I said, tell me what a scalar feed horn, and show me a picture. I want to see one. It goes, great questions. And then it explains what a scalar feed horn is. It reduces side lobes, improves impedance matching, minimizes spillover losses, things that I didn't know about. So in that respect, it's like having a PhD right next to me. And then I go, okay, show me one. So it created this picture. It looks like a scalar feed horn. So I go, and I just kept asking questions. This is a wide opening face the dish. Everybody knows that it does, but it goes, yes. And then it explains why. Parabolic reflector scalar feed horn. I go, okay, so what's the proper measurements for such a horn to be used for radio astronomy? And then it answered, and it gave me the formulas. And let's walk through the core design parameters for the scalar feed horn targeting 420. And it explained the formula, and I checked that. That's okay. 21 feet design, dimensions, optional. It kept giving me answers and prompting me for more actions. So he goes, do you want a diagram of this dimensions on a horn? I say, yeah. So it gave me the diagram in centimeters. Simple stuff. Where's the LNA placed on the scalar feed horn? And then I tell it that it's a Discovery dish LNA. So once again, it went on to explain where I should place it in reference to the dish. And I go, okay, I want a diagram. So it gave me a diagram. Simple diagram, obviously. So to make a long story short, I did this while I was listening to you guys. I don't know if it's absolutely correct, but then again, I'm not a PhD, and it is explaining a lot of things that I didn't know about, and I'm an experimenter. I will experiment with this. In fact, I will build this. So I go, okay, can Can you design an STL file for my 3D printer to build a scalar feed horn? Yes, I can absolutely help you. And it did. It gave me a couple of options. I have a 3D Anycubic Cobra, which is pretty large, but not large enough. So it's going to have to be a split design. And it came up with a split design. So any questions that I have, it gives me an answer. Appropriately, it may not be the correct answer. But this is something that I can always check and I can always experiment. And
So
I don't
Pablo,
need to call.
do you have test equipment to prove that it's correct if you build this thing?
No.
So if you build it, you're just hoping for the best that they got it right.
Yeah. Absolutely.
I think Steve wants you to send him one so he can test it. That's what I heard. Out of that.
No, absolutely not. I don't have the test equipment right now. I can generate the data files and maybe through Ezra and or other programs validate it. But as a beginner, it's giving me some answers. May not be the correct answers, and that's to be once again, I'm not advocating that this is the absolutely accurate, but I'm an experimenter.
It's encouraging, and it's not just spoon feeding you. It's giving you all the formulas. It's giving you the technical background to
gives me the technical
justify
background
its decisions. Yeah,
absolutely. And I go, well, I have an Anycubic Cobra. Well, it's not going to fit there, so we're gonna separate it. And it depends. I mean, anybody can do this. I'm not the only one doing it. I'm the only one paying $20 a month, and I found this GPT. So I'm going to keep playing with this, and it's better than I was doing before, just by guessing what the feed horn was going to be. So and
it
also
probably only took a megaliter of water to cool the servers that did all the calculations, Pablo.
yes. Unfortunately, the reason you guys are so cold right now and it's so hot in LA right now, it's because of me. I'm guilty as charged.
It's a question that's being raised here in Australia too. There's a lot of AI servers that are going to get installed around the cities, and there's concern that the local communities won't have enough water because it's all going to the AI server systems.
Yeah, but I mean, this system's here to stay, and it's up to us to validate it, train it, and use it as a tool. I mean, I don't use a little calculator anymore or a slide rule. I use a computer now. This is nothing but a tool. It's the Star Trek computer, basically. That's what it is. You ask a question, it'll come up with an answer. Is it a good answer? I don't know. It needs to validate it. But I'm experimenting with that. I'm training it. I'm validating as much as I can within my means. And I got now 4 dishes, 2 meters and 2 discovery dishes. And I'm planning on eventually gather all the data and see if this will do something with the data. I don't know how valid it is. And of course you need test equipment to do it, but we are experimenters, and I'm experimenting with the latest technology, which is what ham radios are supposed to do, and I'm doing. So that's all I have to say about that.
Excellent.
May I interject, please?
Go ahead.
My name is Mark Sproul. I'm new here. I recently joined Sarah, and I've had almost identical experience to what he was just talking about with ChaTGPT, designing a feed horn for an 8-foot and a 10-foot dish. It told me what equipment to buy to test it, which I have purchased. I haven't got the feed horns finished yet. I've got them all 3D printed. And I've got to physically assemble them together and put the copper tape on them. And I've got the test equipment to test it, and ChatGPT told me how to test it. The first time when I said to design a feed horn for an 8-foot dish. It gave me a feed horn that was 7 feet in diameter. And I said, that's not practical. And it says, you're right, that's not. Let's do it this way instead. And then went on to do the feed horn similar to what he just did. And it was talking about a loop antenna in the back, which is what I was planning on doing. And it then told me, well, that's going to have to take impedance match because it's 150 ohms instead of 50 ohms. And it said, okay, instead, if you would rather do it this other way, it gave me a different design. And I ended up printing out both of them with the 3D printer. I do have a large 3D printer, a Prusa XL, which is a 14-inch cubed print area, so it can print pretty much the whole feed horn. But my experiences were basically, exactly what he just described.
And when you look into it, eventually you're going to be able to analyze the data, add the data. Maybe it's not going to be an interferometer, but you're going to be able to at least stack the data. It's going to be able to detect patterns, which is basically what they're doing with the large radio telescopes right now, albeit they don't use ChaTGPT. They use their own machine learning systems, but artificial intelligence is everywhere for everything. So it's up to us as experimenters to experiment and validate and eventually train it and use it.
Pablo, when you just Google something now to get an answer to a Google question, AI is the first thing that comes up.
Correct.
I'm sure you've
there
seen
are
that.
many AI systems, Claude, ChatGPT. I mean, it's all over the place. For visual astronomy, there are programs now to get rid of the noise, to deconvolve data. It's all there. It's being used for everything. I use it for medical issues that I have. I use it for legal issues that I may have. You can use it for anything, and it's here to stay. I mean, we can hate it and find fault with it all you want.
Can we get a winning on the stock exchange?
I haven't tried it yet, but if you sent me money, I will try it for you.
For me, it's just basically a really, really good search engine. Is the way I've been writing software for 48 years. In fact, I'm retiring next week. And for me, it's just a really, really good search engine because the search engines these days are so inundated with ads that they're hard to use. And that's what it worked out for me, is just a really good search engine.
And you can talk to it. It's on your phone. It's you can talk to it, ask any questions at any time, and it will be like a normal person answering. Okay, Chad, how many parsecs to the M31 galaxy?
Hey, Pablo, sure thing. M31, which is the Andromeda Galaxy, is roughly about 0.78 megaparsecs away. In other words, that's around 780 kiloparsecs, give or take. So if you want it in just parsecs, that's about 780,000 parsecs away.
Thanks. That's all I wanted to know. And what is the temperature in Australia right now in Melbourne? Do you know?
You're welcome.
Oh, stopped.
It's 14 degrees. Mostly cloudy.
Well, you can ask all kinds of questions.
But that's degrees centigrade, by the way.
Yeah, I know.
Pablo, you mentioned 2-meter dishes. Are you planning on using them as an interferometer?
Well, I'm going to ask ChatGPT to design an interferometer for me eventually to do that. But yes, I have 2-meter dishes in the backyard. I have a large backyard. And I have two Discovery dishes. They're 70 centimeters. And at first, I'm going to add or stack the data to see if I can get a better SNR. And then through validation, I'm going to see if the data, what the graphs that it comes up with, it even comes up with videos of the data. It comes up with anything that you want. Once again,
Would you like to do a presentation for the Long Island CW Club Antenna Forum on this when you get it done?
I am a teacher. Who said that? I'm a instructor
Kim
for
Williams.
Hi, Kim.
Hi.
Yeah, I'm an instructor. I'm an instructor at the LI Long Island CW Club, and Howard already asked me to do a 3-hour presentation on artificial intelligence.
I was just asking about antennas for the antenna forum on Sunday morning.
Yeah, if I have time, I can do that. Yeah. I mean,
That's the problem for all of us these days, isn't it? Time.
Yeah, especially when you get old.
What I'm planning on doing is up to 5 10-foot dishes as an interferometer. That's my goal.
All right. Okay, and I've got a two small antenna phased array that I'm building right now. So we'll have a lot of multi antenna arrays pretty soon. Okay, well, let me keep going. Excellent, Pablo. That was a great, and thanks, Mark, for that update too. Let's go to Kim. Sort of new. What's your background and what kind of projects you got?
I'm a amateur astronomer from age 12 forward, and now at 84, and working with the McMath-Hulbert Solar Observatory in Lake Angeles, Michigan, trying to get it on the National Register so we can save it from deteriorating. And that's the only major project I'm invested in astronomy at this point. My major efforts go to the IEEE, where I'm a past president of the EMC Society there, and that means lots and lots of people depend on me to keep the ball rolling.
All right. Okay. Well, I'm glad you're on with us, and welcome back. And anytime. Let's go, Richard.
Yes. Mainly, I came on today hoping to hear more about the big dish in Australia. Thank you, Steve. I've been doing a little bit of work with my huge 1-meter dish at S-band, trying to do some documentation measurements and see how well it's really working. So that's about it from here.
Okay, thanks. Adrian.
Yeah, I don't have anything to report. Just listening in and congratulate Steve and such fantastic efforts that they've done with the remote control and gosh, that's marvelous. So really amazed. Fantastic presentation. But yeah, that's all I had for today.
Okay. Thank you, Preston.
Okay, thank you. I really have nothing to report. I've been greatly enjoying what others have shared. Thank you.
All right. Now I've got one little video or one little thing to show. I've been trying to get. I'm saying I got a 2-channel phased array or 2 antenna phased array I'm building, and I just had one experience with a one of the new antennas I bought that didn't turn out well. So, and I got myself a nano VNA to test my antennas, and this is the Visuar VS that came off that antenna. But when I first pulled it out, the Visuar was 24, and I went on and asked what that could be, and they said, well, it's probably got a disconnected cable from the antenna. So I pulled it apart, and in fact it was, and resoldered it on and came out with this, and now that's the new Visuar, and that's really from 1 gig to 1.8 gig. So this inflection here is about 1.5 gig. So this antenna looks like it's good at 1420. And so that's what I'm going to use it. But if I pull it out of the box without using this nano VNA, I wouldn't have any idea that I had a bad antenna plugged in. So I'm recommending that anybody with a small antenna get one of these antenna analyzers or vector network analyzers and check out your equipment before you plug it in and expect it to work. So that's really all I've got. And Paul, I'll give it back to you. I think that's everybody.
Interesting conversation all around. I'd just add to the ChaTGPT or the AI discussion. My recent experience, I can't remember whether I reported back to this group, but this was a group of year 12 girls from my school doing international baccalaureate, and they have a theory of knowledge conference, and I gave a presentation at that conference on truth in science. The theme of the whole conference was truth. I took on truth in science, and I gave them an outline of how scientific papers are peer-reviewed and published in journals and cited, and then gave them some case studies of where science has gone wrong. For example, Andrew Wakefield and his linking of MMR vaccine to autism, which is current at the moment, as you might imagine. I gave them these case studies, went through them. Then I said, all right, well, in groups, go off, choose a case study, take it to ChatGPT and see what you can come back with. And this was very encouraging for the students coming through. This is at the top end of school. They really interrogated ChatGPT. They got some fantastic results from them, from ChatGPT, and they challenged and challenged and challenged. They had the conversation backwards and forwards. One group eventually, ChatGPT said, well, that's all I have to offer, you're on your own, basically. They really were able to challenge. So that's very encouraging from my point of view, that those students are not accepting at face value what's coming out of AI. They are challenging it. And I think that's the general thrust of the discussion, that yes, you can put questions in, you can get answers out, but you have to critically analyze what's coming back and experiment, as Pablo says, experiment with what's coming back, and then eventually make your own mind up. So there's a place for AI, there's a place for RI, which I call real intelligence as well, or HR, human intelligence. That's my two penneth, Rich. It's a very interesting area, and as Steve said, every time you do a Google search now, you get an AI response. You have to take that with a big pinch of salt. Make sure it really is telling you something that's accurate. You really need to analyze it before you accept it. But I was encouraged by the students and their approach to AI in that particular context. So I think that's it from this end, and we'll be back together in a month's time, Rich.
All right, that's it. That's it for everything. And I do have one question for Steve about that, about your fans. It's a very technical. It's a very technical one. Is that does your fans go reverse from the northern hemisphere? Just not. I mean, I don't know. I mean,
you've just got to install them the right way around so that it blows in the right direction.
I didn't know. I mean, you obviously swirl up backwards. I just wasn't sure if the fans work the same way. So,
can I share something before we go?
Go ahead.
The other aspect of astronomy is visual observing, and I've got a telescope there. That's my 10-inch, and I still do lots of visual observing. And we had this star party last weekend, as I mentioned, and I did look through some telescopes and some eyepieces. And you may be aware of this new product that's come out on the market. I'll share the screen. It's by Pegasus. It's the smart eyepiece. So this is where the technology is coming to now. It's an eyepiece you put on your telescope, but it's a powered eyepiece, and it does real-time image stacking and image stabilization. So if you just had a standard glass eyepiece, that would be what you would see through the eye with the naked eye, maybe a bit of a fuzzy blob in the middle. Maybe you've only got a 8-inch or a 6-inch telescope, but the optics in this smart eyepiece brings out color, deep sky detail, very faint objects get amplified. It's only worth $3,600, but you don't have to do astrophotography anymore. You can do it in real time. It's an amazing device, and this is where visual observing is going to now. Most impressive.
Well, that's the technology behind the Seastar, Steve.
Yep.
And a lot cheaper than that. They're about 700 Australian.
I have two.
Seastar.
I have two Seastars S50 and one S30 among my 10 telescopes and two roll-off roof observatories, and they're fantastic. I had the most fun with the $400 S30. It's freaking amazing.
Yeah.
No. Yep.
Yeah, I've got an S50. I got it very early on when they first came out, and they're amazing. The only question, some people like the photons that have been traveling through space for 1 billion years to actually fall on their retina. This is a different form of optical observation because you're integrating over time. I don't know those pictures, Steve. What's the integration time?
Oh, I didn't say, but does it matter? I know you're not looking at photons, you're looking at a screen potentially, yes.
I'm just wondering whether it can't be in real time if it's stacking. So,
it's a delayed image, yes.
Yeah,
but it doesn't take long to build it up.
Yeah.
Even the old the iPhones now, or even the Androids, when you do video, they do real-time image stabilization. And that used to take hours of post-processing. You know, you crop the image and steady up the middle part of the frame. So that's common practice to do image stabilization now. So astrophotography, they've gone that next step and made it real-time visual stacking of deep sky images.
Yeah. Well, the Seastar does a 10-second grab. Then you can. It just depends how much patience. So the Seastar's outside, you're inside with your iPad or your computer, and the image just comes in. You can just watch it build, and it's how much patience have you got? You can go for 5 minutes. You can go for 50 minutes, and the longer you go, the better the image.
I set up my Seastars equatorially now, and you can go up to 60 seconds, and it works really well.
Yep.
We saw a little bit of that happening at the Star Party, Paul. There were people who had their telescopes out on the observing field 30 meters away, but they were inside the clubhouse with the lights on and having cups of tea.
Yes. Yep.
Yes. Operating their telescope, looking at the results.
Yes, I do my astronomy now with a glass of wine.
Sorry, guys, I have to leave. I've got a traffic net to meet in just a few minutes. It was a pleasure to meet you all tonight. Thank you.
Yeah, it's been a great session. Thanks a lot.
Yeah.
I'll head off too. Thanks a lot, Rich. It's been really fun.
Yeah, great. Well done, Rich. I think a good session.
Thanks, Paul.
All right, we'll put this on YouTube real soon.
Yep. Okay.
Right.
See you all in a month's time.
Yep. Oh, by the way, we're starting a Drake's Lounge Africa.
Right.
And so that'll start up here probably next month. We got the University of Zambia people that are we've been talking with, and they were even on our Drake's Lounge yesterday, last Sunday. So we're gonna go. Got another Southern Hemisphere group. You guys can deal with, and so hopefully that shows up pretty soon.
Very good.
All right. See you, everybody.
Okay.
Bye-bye.
Everybody.